here we go. Nice thing about this is we did this in the preview. So you have not only seen this, a lot of this last year, but then you will also have seen it this year in this course. That's one of the reasons why we do the preview, is because this is some important stuff, and seeing things more than once really helps. Like seeing it, learning it, taking a break, coming back to it can be a good way of learning, right? So you have seen most of this. Today we're doing simple trinomials, but some other kinds of factoring. Simple trinomials is kind of the bulk of it. And then tomorrow, complex trinomials. And then the difference, we're going to do a third day where we kind of put it all together. And so we'll talk about that on Wednesday, but where we identify the different kinds of factoring when they're all mixed up. Okay, so that's that. Last unit was all about graphing and thinking about like transformations. So does it open up? Does it open down? Does it have a max? Does it have a min? What are the shifts like? We did some actual graphing, but then solving problems that are max-min problems. This unit is all about solving equations. So it's more quadratics, but with a bit of a different approach compared to completing the square, which is how you find the max or min, right? So before we can actually solve, which we'll start solving, I think, on Thursday, so day 4, before we start solving, we have to just make sure we know how to factor, because every time when we're solving, we're going to be factoring first. So we've got to get that skill together, and then we're going to add on the extra step of actually solving equations with it, okay? So factor fully. First question is common factoring. How do I common factor this one? What do I do? Yeah, Ez. Yeah, which is 2. Yep, 2 for this one. No x can come out of it because there's not an x in both. And then how do I write the brackets? Remember we talked about this. Yeah. X minus 3. How did you get that? Yeah, so you're thinking about what goes in the brackets so that if you were to, so this is going to be my check. If you were to re-expand, you'd get back the original question. And that's where I think we're very comfortable with that kind of distributive property. I would imagine everybody, or almost everybody, feels good about that. That feels like an easy question. It's a grade 9 question, right? Just distributing this. So if you relate factoring to the opposite of that, undoing the distributive property, that helps you make that connection of what it is exactly that we're doing, why we're doing it, how it works, and to be able to check your answer and all that stuff, right? This is a check. We talked about this. So you don't want to factor and then redistribute and leave this as your answer. But if you want to do a check, I always say, like, write the word check or draw a line or do it on separate paper. Don't do it like this. Equals. Because that's wrong. Okay? Then you're not leaving the correct answer. So you got to separate that check. But that is conceptually a good thing to do, an important thing to do. Okay? To connect the factoring to the distributive property. You are literally dividing, so when I pull 2 out, I do 2x divided by 2 and 6 divided by 2 to get this. But when it's easy and familiar numbers, you probably will just think about it like, what do I multiply 2 by to get 6? That kind of thing. Okay, easy one. What's different about this one? Yeah. There's an x in both terms. And if there's an x in both terms, or if there's an x in all terms, if there's more than 2 terms, because there will be sometimes, then you can divide it out as well. So TK, what do I divide out?
You divide out 3x.
So 3x, because 3 obviously goes into 3, and 3 goes into 12 evenly, right? You can't always divide out the whole coefficient. Sometimes, like if that was 9x squared, you can't divide by 9. So you have to come up with the largest common divisor of both of them, or greatest common factor, okay? And the other thing that we talked about before, but I haven't mentioned yet, is factoring is a little bit different than some other of the operations that we do, where you have to know what the answer looks like. Like you have to recognize what type of factoring this is, and it's common factoring. I mean, I told you that in the question, but it's common factoring. And that means you pull something out front, and then you've got brackets left over. And it's almost like you're turning it into a distributive property question, but you're not going to actually then expand it again, right? That's not the point. The point is to leave it in factored form. So what do I have left in the first part? I have two terms here, so I'm going to have two terms here. So the first term, 3 divided by 3 is 1, x squared divided by x. You got two x's, you take 1 out, you're left with 1. Positive and positive means it's going to be positive. 12 divided by 3 is 4. I had 1x, and I took out 1x, so I'm left with no x's, so just don't write the x. Okay? You try this one. Go for it.
The answer?
Yeah.
7x bracket 2x minus 3.
So this, yep, that sounds right to me. Everybody else get that? People got that? Yep. So this is an example where you can't divide 14 into 21. Like you can't pull that out. That doesn't divide evenly. So you look for the biggest number that goes into both, which is 7. 7 times 2 is 14. 7 times 3 is 21. And again, you've got x in both terms, so you can pull out an x of each. And this is that kind that's not a realistic one that's really going to come up when we start solving, but it just highlights the concept of common factoring. And it's the only trinomial that we're going to look at. So what number divides in evenly into 20, 15, and 25? It's kind of an easy one, but 5. I've got 2 x's, 3 x's, and 2 x's. So I can take 2 out of each, right? The smallest exponent or the biggest amount that you can pull out of each of them. That's factoring fully. If I only pulled out an x, don't write this down, just watch. I'd be left with an x here, an x squared here, and an x here, and I would still have an x in everything, which means you didn't factor all the way, because I can pull out x squared out of each. And then for y's, it's the same thing, y squared, because I've got a 3, a 2, and a 2. 20 divided by 5 is 4. 2 x's, took out 2 x's, it's gone. 3 y's, took out 2 y's, so I'm left with a y. 15 divided by 5 is 3. 3 x's, take out 2. 2 x's, take out 2. And then negative 25 divided by 5 is negative 5. 2 x's, 2 y's, and 2 x's, 2 y's that we took out, so just 5. So it kind of highlights all the rules, that specific one. There's one particular case where common factoring will come up pretty often. And then there are other cases where it might be a trinomial, but you have to common factor first. So you don't forget about common factoring. It's pretty important. Okay? Any questions about that? We're good? Okay, and simple trinomials, these are the easy ones. We're getting out of the way all the kind of easy ones. And if you remember, I like to always talk about how do we get there in the first place, and that allows us to, again, make that connection to something that we're maybe more comfortable with because you've been doing it longer. People are usually pretty confident with simple trinomials. It's the complex ones that we'll get into tomorrow that give us a harder time. So if I were to expand this, we're not factoring now, we're expanding. What would I do?
X times x, x times b.
And then?
4 times x.
Very good. Right? So we get x times x is x squared, x times 3 is 3x, 4 times x is 4x, 4 times 3 is 12. And then
We simplify.
by,
The x's
yeah,
go together.
yeah, two like terms. So 3x and 4x is 7x. And with this pattern of these kinds of questions that we look at, that always happens. And this is how we learn to factor, is recognizing this pattern and recognizing that these binomials are special. X and a number, x and a number. If it was x and a number and then y and a number, I mean, then it wouldn't follow the same pattern. Or if it was x and y and then x and a number, same thing, like it wouldn't follow the same pattern. Okay? So the ones that we look at, the binomials always look like that. X and a number, x and a number. And when you expand it, you get two x terms that add together, which means I can take that relationship, that idea, and use it backwards to factor. So simple trinomial factoring is two numbers that, what?
Add together.
Add together, in this case, to get 7,
7. Yeah.
right? And two numbers that multiply to 12. So add to 7 and multiply to 12. You got to have both those because there's an infinite pairs of numbers that add to 7, but there's only one pair that's going to add to 7 and multiply to 12. Okay, and then as you remember, I think you probably do, when we have different signs like negatives and stuff, it's a little bit harder. You got to think about the signs, but we'll get to that when we get there. So I'm just going to make a little note again. This is 3 plus 4, and this is 3 times 4. And that's that pattern of expanding. Okay, give that one a try. So did you get x squared plus 10x plus 21? Good. When we notice these patterns in the future, if you had to expand one of these, don't you think you'd just go straight to the answer? Again, because you know the pattern. So you know it's going to be 3 plus 7 and 3 times 7. So you can skip that step. I'm showing this step right now because we're trying to make that connection, and just doing it over and over again is what helps us make that connection, that relationship, that pattern. But in the future, this will also, like this idea of factoring, will also help us sort of skip some steps if we ever have to expand these things, because it's one of those funny things in math that sometimes is hard to get used to. Sometimes we're factoring, sometimes we're expanding, sometimes we want it this way, sometimes we want it that way. So we have to know how to go both directions. And then eventually you have to know which direction do you want to go. So try that one. X squared plus x minus 6. We get that? So this is where we can start to explore the signs a little bit. What do I know if two numbers multiply to a negative? What do I know about those two numbers? They have different signs. One is negative and one is positive. If both were negative, they would multiply to a positive. If both were positive, they would multiply to a positive. So only one of them can be negative, right? So that negative 6 tells me that. And then when I find that the numbers are 3 and 2, and it's positive in the middle, well, it's got to be 3 minus 2, not 2 minus 3. So again, I can use the signs of both those two terms to deduce what the signs of the original brackets would be. And again, that's what factoring is, right? You start with this last trinomial line, and you write out the brackets with the numbers and their signs. Okay, last one of these. Try this one. X squared minus 6x plus 5. Both negative, so they multiply to a positive. But both negative, so they add to a negative. And this is where it's interesting how, like, you know, there's been a lot of debate over the last 5 to 10 years, probably 10 years, I guess, about mental math and how important is it for people to really, like, memorize their times tables and be able to do things fast. And I don't know if when you were in elementary school, did they make you do those math minutes or whatever, those kinds of things? Yeah, some of you probably did. And it can be frustrating if you're not that great at it. But right now, this is where that comes to be useful, because you have to be able to come up with numbers that multiply to a number and add to a number. And that's just mental math. There are ways of doing it on your calculator, but they're really slow. And so when you're factoring, like I said, your calculator can't really just do it for you, right? So that's where this becomes useful. All right, so now let's actually do some factoring. Two numbers that, what? No. This is what we were just doing. Yeah, go for it. Add to 5 and multiply to 4. Very good, right? So that's just the rule. Simple trinomials is more straightforward. This is always how you do it. Add to the middle term or the x term. Multiply to the last term of the constant. If this was somehow written out of order, it would still be adding to 5 and multiplying to 4. That's why we like to write things in the same order every time, because it becomes familiar. Okay? And again, we have to know that when I factor a trinomial, you end up with two binomials. They'll each have an x in the front. It's not complex, so it's just going to be x. That's what makes it simple. X times x is x squared. It's funny how this is one of the harder ones. Does anybody who knows what the two numbers are? Yeah. 4 and 1. Whenever there's a 1 involved, for whatever reason, it makes it harder. I don't know why. Sometimes this is like you're awesome at factoring and you can do complex trinomials and you can do all this great stuff with it. And then you get a question like this and you can't figure it out because it's got a 1 in it. And the middle term is bigger than the third term, than the constant. So just remember that that's my only advice, is remember that there's a tricky one when it's got a 1 in it. And if you're stuck, maybe try 1. Okay, and in this case, both positive because they multiply to a positive, so they have to have the same sign, and they add to a positive, so they're both positive. So again, recognizing what type of question this is. I know the answer is going to look like that. Now I just have to find the numbers. Two numbers that add to 8, multiply to 12. Easy one so far because there's no negatives.
6 and 2.
6 and 2 plus 6 plus 2.
Won't be mad if we switch them together.
If you,
Switch the numbers.
yeah, if you had x plus 2, x plus 6, totally fine. My explanation of that is always 3 times 2 is the same as 2 times 3. Order doesn't matter, right? Order for multiplication doesn't matter. So, yeah, you can write them in either way. What's different about this one? It's got a negative in it. What's the same? Still a simple trinomial because it's got a 1 in front of the x squared term. So it's still going to look like this. And again, this is where we have to use some logic. And you can memorize these things, but I think it's better if you just have an understanding of numeracy. Two numbers that multiply to a negative have to be what? We just finished saying this?
1 positive, 1 negative.
One, don't write this down because I'm going to do the signs at the end. That's how I always do it. You can do it your own way if you have like if it like it's you don't have to do it exactly like me, but this is just what I find easiest. One's positive, one's negative. I know that. I don't yet know which one's positive and which one's negative, but I know they're opposite signs. Which means two numbers that multiply to 30 and have a difference of 7. They subtract to 7. We don't care yet about the order of the subtraction. Just subtract. Okay? So what kind of numbers multiply to 30? 2 and 15? Well, they don't have a difference of 7. 5 and 6, they don't have a difference of 7.
10 and 3.
So 10 times 3 is 30, and 10 minus 3 is 7. And then when you do the signs, I think you're all probably pretty comfortable with this. I know. So if this is going too slow for you, I apologize. But what if I got them wrong? Well, you can always check. What? Go ahead.
Well, your middle term would be negative then.
Yeah, negative 10 plus 3 would be negative 7, which is not the middle term. So if that ever happens, do that quick check. And then just switch them. Right? Just flip them. Always remember that you could get the signs backwards. And if you remember back to the learning goal that we did when we did this the first time around, and the quiz, when this was on the quiz for the preview unit, people did get them backwards. Probably more often in complex trinomials, but people do get them backwards. So keep that in mind and check your signs. Okay, so once again, multiplying to a negative. Therefore, the signs are opposite. So we're looking for a difference of 6. What are two numbers that multiply to 16 and have a difference of 6? 8 and 2. 8 minus 2 is 6. So 8 and 2. But we don't want 8 minus 2. That's positive 6. We want 2 minus 8 because that's negative 6. And the middle term is negative. Okay, try this one. Who's got this one? Anybody else get that? I'm sure you did. Very good. This one is two numbers that multiply to a positive, so they have to have the same sign. So you're adding them. So two numbers that multiply to 15 and add to 8, that's 5 and 3. And then I know they're both negative, right? You could still do the negatives at the end. Whoops. You could still do the signs at the end and say, well, they're adding to a negative, so then they both have to be negative. Still good? That's each type with the different signs in different places. What's different about this one? This is the last one, except I'm going to add one more.
There's a number in front of it.
Yeah, there's a number in front of the x. Well, this is complex trinomial factoring. We're not doing that until tomorrow. What do you notice about this one? Anything?
Question. Can we do it as a common factoring or no?
This is exactly right. You can always common factor if there's something common between all the terms. So all three of those numbers are divisible by 2. So I can pull that out front. Now what do we have? Now we have a simple trinomial. So two numbers that multiply to 36, and because it's negative, they have opposite signs, so they have a difference of 5. You still need the 2 in your final answer. It doesn't go away. What are the numbers? 6 times 6 is 36, but that doesn't have a difference of 5.
9 and 4.
9 and 4. So put the 9 and 4 in there. Do I want 9 minus 4 or 4 minus 9? I want 4 minus 9 because it's negative 5. So we've got that. Adding one in here. Two numbers that multiply to 16 and add to 8. What are they?
4.
Both 4. So how could I rewrite this?
X plus 4 squared.
And the only reason why I want to go back over this is because we did so much of that when we were completing the square. Notice that that trinomial has that relationship. Half of 8 squared is 16. That's how you build a perfect square trinomial. That's what we spent all that time on. And doing all that completing of the square to get the x plus 4 squared to put it in transformation form. Same idea, right? It's just in that special relationship. Do you have to write it as x plus 4 squared when you're factoring like this? No, not necessarily, but we've already seen when you're doing transformation form that sometimes it's useful, sometimes it's a good idea. It's probably a good habit. It's also less writing. You wouldn't have to show that step. If you recognize that you can go straight to that and write it squared, go for it. Less writing, faster, more succinct, all good stuff. Okay? Any questions about that? We're going to do a little bit more because we're doing, like I said, we're doing all the easy stuff today. All good? What's this one? Some people, or maybe most people in here, know how to factor it, but forget what it's called. It's got a name.
Difference of squares.
And it's a difference of squares because 25 is a perfect square. There's only 2 terms. There's a minus sign between them. There's no x on this. It wouldn't work if there was an x. Okay, so that's a different kind of question. So how do I factor this one? Again, you have to recognize that it's a difference of squares. You don't need to know it by name, but you need to recognize it for what it is. And then you need to know what the final answer looks like.
X plus 5, x minus 5.
Okay, so it's a special case. When we come back to this on Wednesday, I'm going to go over this and compare all the different types, and hopefully that will help also recognize when it's a difference of squares. You could two numbers that multiply to negative 25 and add to 0. I've even seen teachers teach it this way. You could do that. The numbers are always going to be the same. 5 minus 5 is 0. That's the only way you're going to get 0 when you're adding, right? So they're always going to be the same. So I think you're better off just recognizing that trick, but you could use the simple trinomial. Okay, try this one. Last example. Yep, TK.
X plus 9x minus 1, 9.
Good. So probably most of us know that 81 is 9 squared. What if you had a harder one? Anybody know what the square root of 289 is? Anybody want to guess? What would it be about? Close to 20. It's not quite 20. 20 squared is 400, so it's going to be less than that. I think you said it. Very good. So it is 17. But you might not know that. Was it? Yeah, it's a good guess. I love it. You might not know that. So, I don't know. It's got an x squared term, it's got a minus, and it's got a constant. It looks like it might be a difference of squares. So I would just check it. Yep, 17. If you get a fraction or something like that, that means it's not a perfect square, so you wouldn't be factoring it that way. That's possible to happen down the road in this unit. But when we're factoring right now, it will be factorable. So you don't have to worry about that. But, you know, you might be suspicious. I wonder if that's a perfect square. Okay, because you're not going to be able to memorize all of them. But that's it. Okay, so 3 types of factoring: common factoring, simple trinomial factoring, and difference of squares. We have seen it already in this course. You would have seen it last year in grade 10, so hopefully it's all kind of reviewed. But again, really important that we nail this stuff, because after today, we're going to be moving on and just using it to do things, not learning it anymore. We've learned it, now we're using it. Okay, so that is that.